If you are investing in aircraft or choosing a career path, you hit a fork in the road right away. Fixed wing or rotary wing. It is a choice between two entirely different ways of moving through the sky. On one side, you have speed, stability, and fuel economy. On the other, the ability to access almost any point on a map and hover over it with pinpoint precision. The desire to master vertical flight is centuries old. We have had concepts for spiral-winged aerial screws since the 1400s, but the mechanical complexity of making them actually work kept them grounded for hundreds of years. To make an informed financial or career choice today, you have to look past the surface-level spec sheets. You have to understand the uncompromising physics of how they actually get off the ground. This diagram illustrates a common myth. It shows the equal transit time theory, which claims air over the curved top speeds up to meet the bottom air at the trailing edge at the exact same time. It is in many textbooks, and it is completely wrong. Basing your operational decisions on flawed aerodynamic myths means you will misjudge what these machines can achieve and what they cost to run. We need to look at the true physical laws of lift. The real explanation relies on two principles. First, Daniel Bernoulli developed equations showing that as a fluid's velocity changes, pressure changes across the surface. Second, Isaac Newton proved that when a moving object deflects a gas flow downward, there is an equal and opposite reaction force pushing it upward. For decades, people argued over which theory was right. The answer is both, and their principles are unified in the Euler equations. This model shows the complete picture. The Euler equations mandate the conservation of mass, momentum, and energy. As air strikes the airfoil, velocity changes create a net downward turning of the entire gas flow. This turning action creates an upward reaction force. That is lift. This baseline physics reality matters because the method an aircraft uses to manipulate these equations completely dictates its real-world capabilities, its operating environment, and its financial cost. Airplanes tackle this physics problem through brute force. They push an entire fixed airfoil structure through the air using constant forward velocity. This cross-section shows the CUDA condition. The airflow meets smoothly at the sharp trailing edge, preventing infinite velocities. Fulfilling this allows fixed-wing aircraft to produce highly efficient, stable lift with low drag as long as they maintain speed. The trade-off for that efficiency is absolute. If the airplane stops moving forward, the airflow stops and the lift disappears. It physically cannot hover. Operationally, this means fixed-wing aircraft are geographically tethered to airports. You need hundreds, sometimes thousands of feet of flat paved runway just to generate enough wind over the wings. The physics of fixed-wing flight perfectly optimizes for speed and economy, but completely sacrifices localized geographic access. Helicopters solve the lift equation by aggressively spinning their blades to generate independent airflow. They force air down over the airfoils, regardless of whether the fuselage is moving or not. This design grants unmatched physical freedom. You can fly backward, crab sideways, and hang perfectly motionless over a targeted location. This visualization reveals a critical limitation: retreating blade stall. In forward flight, the advancing blade experiences high airspeed, while the retreating blade experiences dangerously low airspeed. Push too fast, and the retreating blade loses lift entirely. It stalls, risking a roll out of control. This physical law creates a hard speed ceiling, keeping most conventional helicopters under 200 miles per hour in level flight. Choosing a helicopter means knowingly trading cruising speed and fuel efficiency for the ultimate prize of vertical, infrastructure-free mobility. These same physical laws extend past cruise speeds to define the pilot's cognitive and physical workload. Fixed-wing flight relies on natural stability. Once an airplane is trimmed for cruising altitude, it wants to keep flying straight. A pilot can maintain that path with minimal physical input. A helicopter is defined by multi-axis instability. The pilot manages the cyclic, the collective, and anti-torque pedals simultaneously, requiring constant, unceasing coordination. This workload chart compares the two. Notice the massive spike in the helicopter column. If you adjust the pitch with one hand, it changes the torque, which means you instantly have to make a correcting adjustment with your feet. This inherent instability translates directly to a steep learning curve. Helicopter pilots require a significantly higher financial and temporal investment to achieve basic proficiency. That higher cost extends to the aircraft itself. A rotor system carries an incredibly high volume of moving parts, linkages, and bearings compared to a fixed-wing turbine. This mechanical complexity drastically increases hourly maintenance costs, inspection requirements, and fuel burn. This map visualization shows the limit on maximum effective range. Helicopters cap out at a 400-mile radius, while a fixed-wing aircraft easily travels over 2,000 miles. Factoring in slower cruising speeds and mandatory fuel stops, the helicopter's cost per mile skyrockets. For any trip over 300 miles, choosing a helicopter results in severe financial and temporal penalties. A fixed-wing aircraft is the mathematically logical choice for distance. This decision tree aligns investment with the laws of aerodynamics. It starts with one question: what is the primary mission constraint? If it's covering distances over 300 miles quickly, the path leads to a fixed-wing airplane. This is the required path for commercial pilots, business travelers, and cargo operators. But if your constraints require hovering, precise maneuvering, or operating without runways, the second path leads to the helicopter. Choosing this path means knowingly accepting the premium in training costs, fuel, and maintenance. That is the price of admission for geographic freedom. In specific industries, the helicopter's aerodynamic trade-offs are an absolute necessity rather than a luxury. You cannot land an airplane on an offshore oil platform. Medical evacuations and search and rescue teams rely entirely on the rotary wing's ability to maintain a perfectly stable hover over complex terrain. There are hybrid designs attempting to bridge this physics gap, taking off vertically but cruising on fixed wings. But even these machines cannot cheat physics. They achieve that versatility by paying the complexity and cost penalties of both systems combined. Success in aviation investment, whether time, money, or career, requires accepting that you cannot fight fluid dynamics. You must simply weigh all the operational constraints and choose the specific aerodynamic trade-off that perfectly matches your mission.